We start from where we left, and we were trying to develop the relationship between emission and its impact. Okay. So if you recall, we're talking about the flux, okay, flux of the pollutant, okay. And first thing we said about the flux of pollutant was, number one was, which flux? Advection flux, okay. Flux due to flux of what? Pollutant, okay. Okay, and we define that as JA, okay, that was equal to CU, okay. And there was another kind of flux which we defined more because of diffusion, okay, more because of diffusion, okay, and that we call flux due to diffusion, and that we say JD, right, okay, that was negative diffusion coefficient. Did we say dx or we said simply d? Okay, we'll write it d. D, then del C del x. Want to utilize them now, okay, to develop some kind of relationship or something called equation of continuity or equation, advection diffusion equation or something. So for that, let's see, suppose I have a strip and we'll try to do it in one dimension. Okay, and my flux is in this direction, okay, and the area is A, okay, and the direction, this I am calling this as x, okay, the width of the strip, okay, let's call that as the delta x, okay, and then C is a concentration at this point, okay, C here, okay, that is at x and t, okay. C has two domain, okay, the concentration, it can be function of x and it can be function of t, okay. And here on this side of the strip, C will be at time x plus delta x and t, okay. Just to make it more clear, I can, even if you like, I can make it little look, to give it a solid look. Okay. Now I want to write the mass balance about the strip, okay. Writing mass balance. So I can say the accumulation inside the strip is input minus output and say the flux which I am talking about here is, let's say, J. Okay. So what I can say about the accumulation is the concentration at x times T plus delta T minus concentration at x T. Okay, that is a change in concentration you have. I must convert this into the mass per time. Okay. So what do I do? Area times del x. Okay. And time is delta T. That is the accumulation part. Okay. All right. This is something, again, something similar to del C by del T, but we are talking against this strip. Okay. The concentration, we are talking accumulation. How much is accumulation rate? Okay. Concentration at T plus delta T minus concentration at T times delta T. So concentration per second or per time, but we are interested in mass balance. So area times delta x. Is that all right? Okay. This must be equal to, I can take the advantage of J now. Okay. What do I do? J at the time at x T, okay, and minus J at x plus delta x. Okay. What do I multiply here to get the same units as this one? Flux is what? Mass per time per area, right? And what I want is mass per time. So I multiply by area here. See here if you agree with this. Is it all right? Well, we'll do it once again. J. What are the units of J? Mass, area, second. Okay. So if I multiply by this area, I am getting mass per second. Mass per second in, mass per second out is mass per second accumulated, right? That also is mass per second, mass per second, mass per second. Okay. Is that right? All in agreement with me? Okay. So this area will go off from here. Okay. This one, if you agree, I can write this as T. Okay. Times, let's say I am still maintaining the delta x here. For J, what can I write? This plus this, that is the total flux. Flux due to advection and flux due to diffusion. Okay. So if you agree with me, I can write here Cu, okay, minus d. Okay, since we are writing still in delta, so I'll write this as delta C over delta x. Okay. This is evaluated at what? At x. Okay. So at x minus Cu minus d del C over del x, delta x rather, evaluated at x plus delta x. Any problem so far? Yes? In this, in here? What is saying? At the outlet? x plus delta x. Uh-huh. See, where is it? Where is the C I am talking about? Concentration is in the strip. Concentration is in the strip, not at the faces. Right? The concentration is in the strip, not at the faces. I am not talking about the faces. Concentration is in the strip. So that how will concentration in the strip will change? So concentration strip will only change because of change in time domain. Okay. So this is concentration, this accumulation in the strip. Okay. If you like, in strip. Okay. And then suppose if we take the limit delta t tends to 0, delta x tends to 0. Okay, let's see what we can write. Okay. Okay, so this I have this minus this, so I am getting this as the minus, that will be plus del x of d del c by del x. See if you are getting the same expression or not. Okay. You also have to make sure what I have written is correct. Okay. Is it minus sign? You see everyone how the minus sign comes here? For derivative, it is derivative at x plus delta x minus the concentration at x, whatever. Okay. But this you see here, this you have, this term is plus. Okay, minus this, or have we got it the other way? We got the other way. Let's see, we'll do it again. Okay, let's see. Should be minus. Do everyone see that? That will be minus? Or we need to do some expansion? You see that's minus. Very good. So this will be minus. Alright. Or minus. Suppose I say u is not function of x. It means if I am traveling along the direction x, the wind speed does not change in my case. So that is the approximation I am taking, or that's the assumption I am making. So u is out, del c by del x, and I am also saying the diffusion constant is not function of position. Okay, so this also can be taken out. So d or plus u del c by del x minus equals to 0. And if you agree, I can write a three-dimensional form of this one. Okay. But before we do that, you recall this d, we are taking this as the molecular diffusion. Okay. So now this d will replace it with the turbulent diffusion, because in the atmosphere most of the time we encounter the turbulent diffusion. Okay. hoping that the theory remains the same. So I can write this plus u del c by del x minus normally the turbulent diffusion we are talking in the x direction only. So that is, I can write the turbulent diffusion coefficient kx note that kx is the turbulent diffusion or the diffusion term in the atmosphere, and the units of the kx will be the same as that of d, because we are simply replacing the d phi k. Okay. Now if you agree, I will generalize this equation in the form of 3-dimensional equation, because our air thing is always 3-dimensional. Okay. This equation is valid even for the water system. This will be valid even for the river system. Okay, 1-dimensional thing, but we will make it 3-dimensional and try to write in 3 dimensions. So okay, minus kx square c by del x square minus ky del square c over del y square minus kz okay, and this what is our 3-dimensional advection diffusion equation. Okay, this is our 3-dimensional advection diffusion equation. And what you can do is that if you agree, I can write that these terms together are my advection term, or which is causing advection diffusion and advection transport, and this term I can write this term as diffusion or turbulent diffusion. I am not using the word turbulent diffusion, what is that? Okay. Here we have not added the term source and sink. Okay. To keep the life simple, we have not added the term source and sink. We are not adding any more emission, okay, as a source, but soon we will do that, the same thing. Okay. Some of you, now let me explain. U is the velocity in the x direction, V is the velocity in y direction, and Z is the velocity, W is the velocity in the Z direction. Similarly, the turbulent diffusion coefficient in the x direction, in the y direction, and in the Z direction. Clear? Okay. And to give you a little feel of the system of coordinate system, this is system. This is our x direction, this is our z direction, and this is our y direction. Okay? Okay. Now what I want to do is, some of you know about have you heard about plug flow reactor? Have you heard about plug flow reactor? Okay. In plug flow reactor, there is no diffusion at all. It is only the advection. Okay. So if I want to write the diffusion equation or the equation for the plug flow reactor, I'll say this term is 0. Okay. And if I say, suppose I have taken a big box, okay, okay, and I have put some ink or something to disperse, and so there is no movement of the fluid from the box, and I am shaking the box. So I am causing the turbulent diffusion, but there is no movement of the fluid as such. The velocity is 0. So if suppose I take a box and put some, let us say, ink or something, and I am shaking it, so then that equation that will be valid will be, these all terms will be 0, right, the advection terms will be 0. So that is what you can modify this equation, which is very generalized form of the equation. You can modify depending on what situation you are talking about. Okay. Let us having said that, our idea, or if I can say, this is mother of all equations that we need to know, okay, and from there we will make many assumptions and try to solve it for the concentration part. But then if you agree with me, these equations do not have an analytical solution. This partial differential equation does not have an analytical solution. Okay, once the equation is not solvable with your conventional differential equations, that the methods which you use, how do we solve the differential equations once we do not have the analytical solution or closed form solution? How do we solve them? We solve them numerically. Okay, so one way the people went about solving this equation, okay, is to solve it numerical solution. So one way to solve this equation is the there are many methods through which you can solve it. For example, finite difference. Okay, you can use the finite volume or finite element, that is more commonly used. Okay. What is the advantage of numerical method? The advantage of the numerical method is you are using the exact equation, okay, equation which you derived from basic fundamentals. Okay, you are not tampering with the equation in any form. You are not making any assumptions. Okay, so you solve. Okay, solve an exact equation. Okay, disadvantage, you need sophisticated computers, okay, computer time, and second, solution will always be approximate. Numerical methods will never be 100% true. So if you say I'll use the solution is inexact, okay, then I can write here solution of equation solved through numerical means is solution is inexact. Okay, you will always agree with me. Okay, if that is the case, but then there are analytical methods also, if we can solve it. Well, in this case there is no analytical solution, but I can make some assumptions. I can simplify the life and then solve it. But in order, once I simplify the equation, is the equation exact? So the advantage is, okay, of this one, advantage of such method or the analytical method is, we are talking in context of this equation, don't forget that. The advantage is simple. Well, sometimes it may be so simple as you don't even need the calculators to solve if you have the closed form solutions. Simple, but advantage is very simple, but the disadvantage is to start with equation become inexact. Simple and exact, but you started with equation is inexact. Okay. So there are two ways to solve it. This one we'll talk little later. Okay. After a few things which we have covered, we'll do one example as to how this equation we can solve it numerically. Okay. You should have the idea how this can be solved numerically. But the focus of the coming lectures will be on to how to get the analytical solution of an equation that we can simplify and can get a analytical, or sometimes also called as the closed form solution. Okay. So then I have to make certain assumptions. Okay. So our now objective is to get the analytical solution. To get the analytical solution, I must simplify, and to how can I simplify? I make some reasonable assumptions. Okay. So we make some assumptions. Assumptions to simplify the advection. I can write this as advection diffusion equation. And you see the assumptions which we will make. Okay. Assumption number 1 that I will make, and I will see the impact of that assumption in my equation that I have written on my left hand side. Compared to u, okay, what I am saying now is the cross wind direction. Okay, my x is the wind direction. Okay, so compared to my wind in the x direction, what do you think the wind will be in the perpendicular direction? Almost negligible. Okay, so I can say the wind in y direction or more commonly we write cross wind direction is negligible. What do I do? Drop this term. Okay. What do you say about W? I can also say the vertical winds will also be negligible. Okay. So assumption number 2, wind in z direction is negligible. Okay. These are important things to understand, as to which I'll get a solution which will use very frequently, or if you stay in air pollution field, you will use it all your life long. But then you should know where that equation has come from. So then if that is the case, I make this equals to 0. Okay. All right. I make another assumption. See, a body is being advected in the x direction, okay, and at the same time body is also diffusing in the x direction. Okay. Suppose if I have a air, okay, which is air pollution, which is formed as a circular thing. So you see here at some point, and it is diffusing in all directions. So this will become bigger because of the diffusion. Okay, as it travels, it become bigger and bigger because it is diffusing. But when we actually see it, okay, it remains same in this one, but you see here it diffuses much more in the x direction, and that diffusion is because of the advection, okay, because we have dropped the advection terms in y and z direction, but here you see this term which is the advection in the x direction, this is my x direction, okay. So the term advection is overwhelmingly large compared to diffusion in the x direction. Did you understand what I said? Okay. The diffusion due to advection in x direction is overwhelmingly large compared to diffusion because of the turbulent diffusion in x direction. Okay. So the third assumption I can say, looking at those things, is my, if you agree with me, u del c by del x is much bigger than what? Kx del c by del x square, much bigger than kx agreed. Okay. So I'll apply my assumption there and drop which term? This term compared to this. So this term I put this equals to 0. Okay. Fourth assumption, because I must keep on simplifying until I can solve it. Okay. The fourth assumption I can say steady state. Steady state condition, and you all know the derivative with respect to time should go to 0. Okay. All right. And other implicit assumptions, you all know about this one, that dispersion coefficient are not function of time, they are not function of space, and the another important assumption which is implicit in this one is a u, the wind speed in the direction x is neither function of time nor it is function of space, right. So don't forget, let's write so that you have it with you. A u, I'll write a little mathematically, is not function of x and t. So when there is a constant wind that you are kind of facing all the time, okay. Once I make all these assumptions, I'll rewrite that equation, okay. That term is gone, so I have minus, this term is gone, ky c over del y square minus kz 0. Okay, a simple equation. Okay, and there are ways to solve this equation, as you can figure it out from the books or from the various methods that are available, and then I'll write a general solution for this one, so that what I want to find out is C. Don't forget, my interest is to find out the ground level concentration. So the general expression for this one is C equals to a big K, let's say, is a constant, exponential minus, okay, y square ky plus z square kz times that is what is the general expression I get. I promised you that we will make some assumptions and solve this equation analytically. Okay? Suddenly life becomes very simple. You can do anything and everything with little calculator or with your log tables, and forget about solving it numerically. But don't forget, to get to that thing we have made many assumptions. Okay? Sometimes the assumptions are correct, sometimes they are not so correct, but anyway we have simplified the equation. Okay, now the challenge is to find out the K. Okay, For any differential equation, when you want to find out the constants, we need some information on the initial boundary condition or the boundary conditions and things like that, and I will discuss the boundary condition which will help me to find k. Okay. Okay, now I am making something, okay, or let me draw the picture, that is even better. Okay, and suppose, let's do this. I have a chimney and this coordinate is 0, 0, 0. To make the things a little more clear, I can also say what are the coordinates of this point? Don't forget, this is x direction, this is y, and this is z. So this coordinate of this point, just for the sake of understanding, so that we understand our coordinate system very well, because this we will use several times. Okay, is my, if you agree, I can write this equals to, right, just to give you a little feel of this one. Okay, and let's say this is my chimney. Now I am introducing a source. So far we have not talked about the emission source. So now I am introducing a source. Okay, and I have a plane perpendicular to the x direction. Okay, imagine a plane which is perpendicular to the x direction, and that is kind of extending infinite in the y direction and infinite in the z direction, but cannot go negative or z direction, because this is the ground level. Don't forget that this is my ground level. Okay. So if that is what is my plane, infinite plane, okay, and if I take one strip this way in the plane, the other strip this way, okay, this will be my dy and this will be my dz. Let's see. So the amount of the q, the emission rate here, I am calling this as a q. Q is the emission rate in mass per time. And so if you will agree with me that dq passing through this strip, okay, will be nothing but u times c dy dz. Okay. If I integrate from both the sides, u, as I am saying, is not the function of anything. Okay. So okay, y I integrate from minus infinity to plus infinity, because it can go this direction and the plume can go this direction. Okay. So this is minus infinity to plus infinity. Okay, and this is double integration, and z I can integrate because nothing will go below the ground, from 0 to minus infinity, let's say 0 to minus infinity, and then so I have to write c dy, okay, and this will be equal to nothing but in y direction what? I'm sorry, my mistake. All right, thank you. Okay, so this will be nothing but equal to q. This will be the entire amount of that q that will flow through that plane. So that is my total emission rate. Okay, which is known to me. I know how much is the emission that is coming out from a source. I can say so much is the emission coming out from the Panki power station, for example. So Q is known to me, okay, and if I put in place of this C, I can put this expression, right? This is my C. Integrate this one, okay. Find the value of Q, find the value of K in terms of Q, okay. Is everyone see what I am doing? I take the value of C from that equation, put that expression here, and I can find the value of the constant large K or big K in the form of Q, okay, and that constant comes out to be, where do we write? With this boundary condition, my big K equals to we'll check this thing because we are not deriving it fully. Okay. So if you agree with me, I'll take little advantage of what I am writing here and call this as C and multiply with this one. We write the exact same expression which we are getting. Minus y square. All right, I can write this one. I want to define something else. Okay, I want to take a little bit of statistics, and we say the normal distribution. Okay, suppose leave this one for the time being. Suppose I want to find out the probability density function or joint probability density function of two random variables. I'll just give you an example, y and z. Okay. Okay. How do I get the joint probability density function? I simply do joint probability density function, or let's say variable y and z is simply so. If you will agree with me that what I can write is let's say another assumption I am making is that mean so I am writing is a joint probability density function of two RV. RV stands for random variables. Okay. Okay. Now what I do is, so this is my equation 1, this is my equation 2. I compare my equation 1 and 2, okay, and let's say if I can do something, okay. So I look at this part which is inside the exponential term. Let's say if I can, if you agree with me, let's do a few things. Ky, that is coming from there, or rather 1 upon ky times u upon 4x. We are comparing that, so I just need some space here. So 1 upon ky times u upon 4x is equal to sigma y square. I'm just comparing that, and it is just, these can be just scaling parameters here, but then it's essentially joint probability density function, and I suppose I equate this, and correspondingly I'll change my other things also, okay. So I can do that, okay. So in place of this, okay, in place of this, what, and similarly if you agree with me, I can say 1 upon kz equals to 1 upon kz times u by 4x equals to okay. So this ky will be equal to u upon 4x to sigma y square, okay. And kz will be equal to 4x to sigma z square, okay. Or now based on this understanding, based on some statistical comparison, okay, can I rewrite my equation 1 in terms for C, okay. So C equals to q upon 2 pi ky times kz, okay, and then the square root. So what do I get? You see here the x will cancel, right, okay. The 2 will come out, and then sigma y sigma z, and u will be square, under root of u will be u, okay. So what I can write here is, okay, u the x will cancel, right, and the 2 also will come. Let's say let me write 2 here, and then exponential, yeah, the 2 will go up, okay. Exponential minus and this is what is called your Gaussian model. Okay. Okay, from a continuous source. Okay, so this 2 will cancel, so let's take this one out. Okay, this is a Gaussian model for continuous. Why we call it Gaussian? Because our expression that it came out to be, it was in the Gaussian form. See here, this is equivalent to the Gaussian distribution. Okay, this came in the Gaussian form. Somebody very quickly tell me what will be the units of sigma y and sigma z. Because dimensionally this is an analytical solution, the units must match. Units of sigma y and sigma z. Meters, length units, good. And we'll little bit go more into this one, explaining a few things. And you see here that when I want, and this what the C is, where am I trying to find out C? I have not lost the feature of 3-dimensionality in the whole thing. I made some assumptions, but my equation or my model is valid in 3 dimensions. Okay, so my this C will be at any value of x, y and z. Okay, what you see here is this one. And now we'll explain you the meaning of what is sigma y, sigma z. But quickly tell me that where has the x gone? Because here I want to find out the concentration with respect to x, right? Where is x? X somehow is the way we define sigma y, sigma z. X is inbuilt in sigma y and sigma z. So always remember the sigma y and sigma z will be function of x, right? Don't forget. Okay, sigma y, x is disappeared from here. Okay, but x is disappeared because my sigma y and sigma z will be function of x. Okay, and similarly my dispersion is lost. Where has it gone, my dispersion? It is in some formation of sigma y and sigma z. Okay, so that we'll see. So can you quickly, before we end the class, sigma y and sigma z will be function of x and ky and kz, and ky and kz are function of turbulence, right? And in our case, so far what we have done, turbulence, we are defining turbulence as what we are defining the turbulence as atmospheric stability. Recall? Okay, so see the connection here. X is inbuilt between sigma y and sigma z. Sigma y also represents ky and kz. Ky and kz are the turbulent diffusivities, and turbulence I am defining as per my earlier classes in the form of the atmospheric stability. So sigma y and sigma z, we conclude that sigma y and sigma z, they will be function of downwind distance x, including z also, sigma z also, function of x, and turbulence. And this turbulence, so far we have discussed, and so far the way we have talked in the class, depends or defined by atmospheric stability. That is why we spend so much time explaining stability. Okay, if there any question, I like to answer.
So the turbulence that we are taking, it incorporates both mechanical turbulence and thermal turbulence?
Everything.
Sir, how we separate that, sir?
How we separate that? Either we need to separate that, okay, or we somehow find a composite way to find that one, right? okay, because ultimately we want to find out the C. Okay. So that how to find out that turbulence, which is mechanical, thermal, or because of the kinetics and things like that. So how to do that one, that we'll see, but that by and large that will be governed by the atmospheric stability. Okay. How it is governed, that we'll see later, but as I say always in the class, we have the qualitative and quantitative. At least in the qualitative sense, what function it is we don't know, but you will agree with me the sigma is y and sigma z are a function of x and turbulence. And turbulence we have defined that as the stability so far in the class. And stability we can find out through the many ways. One of the ways was the Turner method to get the data from the airport and find out the stability from any place in the world. Okay, we'll stop there. Thank you very much.